Okay, so in this video, which I think will probably be the last one, I want to use what we did last time. So if you remember at the end of last time, we found that WNK of x is approximately, let's see, 1 over square root of 2 pi n times the square root of 1 over x1 minus x. Oops. Right. If x is sufficiently close to k over n, or if k over n is sufficiently close to x. Right. So again, the reason this was what we had last time, and we were thinking of x as being the variable, and we maximized WNK just using calculus, and found that this was approximately the maximum. And we were sort of, this is phrased in a way that where you think of x as the variable. But if you kind of flip it in your head and think of k as being the variable now, then it's like if you fix an x, then whenever k over n is sufficiently close to x, this will be true, right? So then what I want to show you is like, okay, so consider the sum from k equals 0 to n of n choose k, of just WNK of x, okay? Just WNK of x, right? Which we showed was 1 before, right? So suppose we isolate the terms from, so where, let's say nx minus 1/2 square root of 2 pi n square root of x times 1 minus x is less than k, less than or equal to k, less than or equal to nx plus 1/2 square root of 2 pi n square root of x times 1 minus x. Okay, so so let me go to a new page here. So consider the sum from k equals nx minus, let's say the sum, where k is nx minus square root of 2 pi n square root of x 1 minus x to nx plus square root of 2 pi n square root of x 1 minus x of WNK of x. And of course these, so I'm going to maybe replace this with like approximately, right? Or if you want, you could take like a floor or ceiling or whatever. It doesn't really matter. Okay, even though these are not integers, okay? Just take like whatever the nearest integer is and use that. So, whatever, floor, maybe, let's use floors or something. I don't want to get too caught up in that, right? So, so note that like, okay, in this sum, k over n ranges from, right? So if we divide these two things by n and look at the range of values of k over n, we get x minus square root of 2 pi. Wait, let's see. Oh, sorry, there should be a 1/2. 1/2 here. So these are 1/2, and this is, there's 1/2 over here, right? So we have 1/2 here. So x minus square root of, so we have like a 1/2 square root of 2 pi square root of x 1 minus x over square root of n to x plus 1/2 square root of 2 pi square root of x 1 minus x over square root of n. So for large n, this means k over n is very close to x, okay? Because look at this. We have this a range, right? K over n stays within a range around x that is that's like proportional to 1 over square root of n. So as n gets really, really big, k over n is like forced to be very close to x if it's within this range, okay? Right? So if that's the case, then we can kind of use our approximation here. So this sum, right, from k equals whatever to whatever of wnk of x is approximately the sum from k equals whatever to whatever of, what was it? So, right, 1 over square root of 2 pi n square root of 1 over x 1 minus x, right? Approximately. But if you look at this, this doesn't even depend on k anymore, right? This is just a constant. So this is just like the number of terms times 1 over square root of 2 pi n square root 1 over x 1 minus x, right? But the number of terms by design, right, this is, the total number of terms would be something like the number of terms is approximately nx plus 1/2 square root of 2 pi n square root of x 1 minus x minus nx minus 1/2 square root of 2 pi n square root of x 1 minus x, right? But then, right, when you do this, you just get square root of 2 pi n. So this is just square root of 2 pi n square root of x 1 minus x, okay? So this is square root of 2 pi n square root of x 1 minus x. So this is overall approximately 1, right? So what we're saying is that basically, so the moral here, almost all the weight, the weight of, almost all the weight of the WNK is concentrated in the terms between, nx minus this, whatever, square root of 2 pi n square root of x 1 minus x and nx plus 1/2 square root of 2 pi n square root of x 1 minus x, right? So, right. So, so the point is, okay, so if we, so basically if we split the sum, the overall sum, right, for Bn f of x into like the sum where, so I'm actually gonna kind of, well, yeah, I don't know. So k close to nx of f k over n wnk of x plus the sum where k is far from nx of fk over n wnk x. We expect this to be approximately f of x and this to be approximately 0, okay? And when I say k close to nx, I mean like k being within these bounds. So basically it's like you take the terms where k is within these bounds of like, you know, something proportional to square root of n away from nx, and you put those in one sum, okay? And then you take all the rest of the terms, okay? It's like all the other terms in the series that are not in this one, you just put them in this one, and because k is far away from nx here, then you should be able to control this and make this close to 0, right? And that's effectively what the proof in the book is doing. And one thing I want to point out is that, like, okay, to control, right? So to control, like the what is it? So right. Okay. Well. Okay. So overall, all right. Let me do this. So overall, we have. So this is kind of like the integral situation too, where you split up. You kind of like look at the difference, and then you split up into these different regions. So the difference between like f of x and bn f of x, right? F of x you can write as like the sum from k equals 0 to n of f of x wnk of x. And then this one is the sum from k equals 0 to n of f of k over n wnk of x, right? And then this, right? So let's just combine these series. So this is this k equals 0 to n of f of x minus f of k over n wnk of x, right? And then now let's use the triangle inequality. Then we have f of x minus f of k over n wnk of x, right? Oops. So then the point is, right, we can split this into two series. So this is k, let's say k in a of f of x minus f of k over n wnk of x, and then plus the series k in b of f of x minus f of k over n wnk of x, right? So if you split this, this is like the close to nx, quote unquote, and this is like far from nx. Okay, so here the point is like this is small if so if we choose a delta, right, and then okay, well actually I'll explain that in a second, sorry. Hold on. So but the point is that we can control this to make this term, so the first term, we make this small, okay? We make this small here. And then in this term here, we can make this, so this we can bound above by like some, you know, using an upper bound for f itself. And then we make this small by making the sum over k and b of wnk of x small. And the way we make this sum small is by making sure that we put enough of the terms in A, right? Basically, we put all, like, basically that B can only contain the terms like outside of this range, you know, of something proportional to the square root of n around nx, basically, right? So the constants here are all like kind of slightly off from what you'll see like in the textbook. You won't see these like square roots of 2 pi floating around and stuff like that. That's all like, you just don't worry about that, okay? And also this like square root of x 1 minus x thing, there's like a sort of annoying or like complicated reason why that can sort of go away, but effectively it's like you should think of this range as being something, there's like a range of width proportional to square root of n around nx that k can be in, to be in this like close to nx set, basically, right? And that makes k over n be in a range of width like 1 over square root of n, something proportional to 1 over square root of n around x, right? So basically the point is, okay, first we want to choose a delta to make that we'll use to like make this small. So it's like first choose a delta that we can use to make f of x minus f of k over n small when k over n is close to x, right? Like when k over n is within delta of x, we can make this be small, right? Then pick n large enough so that like, you know, let's see, whatever, you know, this like, let's just use this range here, right? So it's like we want all of the k over n's in this range, right? To be, so let's see, k over n is ranging between these two values, right? So the distance away from x is like whatever this is. So 1/2, whatever, root 2 pi root x 1 minus x over root n. So let me do that. So like 1/2 root 2 pi root of x 1 minus x over square root of n is less than delta for n greater than n, right? The point of this means that f of x minus f of k over n is small for all the terms in the A series, and the sum over k and b of wnk of x is small too. And the reason this is small is just because we chose A so that like all the values of k outside of A make wnk very, very small, okay? So what you can see here is that in this choice here, right? So in choosing n this way, we have chosen, oh, and also I guess there's like this like what 2m here. So so also choose, let's see. So also choose, well, yeah. So the capital M in the book, you'll see that their choice of like capital N involves capital M. And it's just the way I've described this is too loose for you to see how that happens. But the important thing is that, okay, so, right, if you just multiply by square root of n and divide by delta, then there'll be some constant up here, let's say, because this is like less than, you know, like the biggest this can be is like 1/2. So right? So as long as we choose like 1/4 the square root of 2 pi over delta to be less than square root of capital N. So let's say like 2 pi over 4 delta squared is less than n, or some constant over delta squared is less than n. Right? But the point I'm trying to make here is like, okay, again, okay, so I've kind of left out a lot of like stuff because of the fact that I'm not actually like approximating what like how much stuff there is left in this series here. So if I were approximating that, then those factors would end up getting incorporated into the choice of capital N as well. So like m and the epsilon that we're given would also factor into this, and you'll see in the book's proof like their choice of capital N. So in the book, they choose n to be like capital M over epsilon delta squared. Okay, so the capital M and the epsilon come from doing a more delicate analysis than what I just did. Okay, and that basically the more delicate analysis involves like actually estimating how much stuff is left over in the series of WNK over K and B, like how much stuff there is in here. And then also like how basically, yeah, like how big this can be too. I mean, that's all involved in like estimating this series. So that's how they choose their capital N. But the point is you can see this relationship between delta and capital N, that capital N has to be chosen sort of proportional to 1 over delta squared, especially. Okay, you'll see that in the book too, that their capital N involves a 1 over delta squared factor, and that we got that just from doing this kind of very heuristic analysis. I think is speaks to the that the fact that this analysis has given us real insight into how this works. I also want to just point out before we finish this that, or before I sign off, that there are a lot of like similarities between what I just outlined here and what I talked about in the second part about probability stuff, right? And also it with similarities with what they do in the book, okay? That like ultimately in their argument in the book, they literally do this they do this trick of like splitting the series up into these two sets, okay? And like basically, so in the real proof, the sum over K in A of f of x minus f of k over n WNK of x. Of course, they use like, they don't use my notation of WNK, but I'm just using it for efficiency, is analogous to the integral from x minus delta to x plus delta of f of x minus f of y p and tilde of y dy in the probability version. And the sum over k in B of f of x minus f of k over n WNK of x is analogous to the integral from 1 or from 0 to x minus delta of the absolute value of x, f of x minus f of y p n tilde of y dy plus the sum from the integral from x plus delta to 1 of f of x minus f of y p n tilde of y dy. Okay, So the analogy can be made very kind of explicit, and actually, like, you can see that this like this plays the role of f of y. This is obviously f of x, and this is like Pn tilde of y, where y is like k over n in the analogy, right? So basically, yeah, I mean, the structure of the proof as they lay it out is like actually very similar to what I've described, both in the probability form and in what I just talked about in this video. The very last thing I'll say is just like, okay, this lemma they prove about, so their lemma in the book about like this sum from k0 to n of nx minus k squared, n choose k, x to the k, 1 minus x to the n minus k, is nx 1 minus x, which is less than or equal to n over 4, is their way of bounding the sum of over x in B of Wn k x above by basically something proportional to 1 over n. Because basically, if you think about it, this term here is small. This term is like very small when x is close to, so this is 0 when, or it's small, let's say. Actually, let's let me like factor this out. So like let me factor out n squared from this. So let's say 1 over n squared, and then, or sorry, let's say n squared, and then x minus k over n. So this is approximately 0 when x is approximately k over n. So that's in the A series. But so but it's in the B series, this is actually like, you know, some larger number basically. But if you divide both sides by like, yeah, if you divide both sides by n squared, you'll get like a 1 over 4n here, right? And so basically that's, you know, yeah, that's how they deal with the B series, is like this is like not small. This is not small when k is in the B series. So maybe I should say that. So this is not small for k in B. And so that way you can actually use this to say that, like, okay, the actual sum over, sorry, this is not x and b, it should be k and b. The actual sum over k and b of w and k of x has to be pretty small. If these are not, this is not actually a small number, then like that means that these numbers actually have to be pretty small in order to make this bound work out, right? So yeah, this is like bounded, you know, below by something. So that means that you can bound the actual sum above by something proportional to 1 over n. If you take a lower bound for this and then divide the whole inequality by that lower bound, or sorry, yeah, yeah, something like that, then, or yeah, if you replace, sorry, if you take yeah, a lower bound for this, then right, then the series, right. So then the series, if you replace this with a lower bound, then and then divide by the lower bound, the series of wn(k) of x will be less than or equal to this thing with the lower bound, and then so it'll be less than or equal to 1/4n times the lower bound. So yeah, anyway, that's all for this video, and that's all for this lecture too. I do hope that this helped shed some light on where all the stuff, like when they choose their capital N in the book, they literally say let n be capital M over epsilon delta squared. This choice of n is unmotivated at this point, but we make it here to emphasize that it does not depend on the choice of x, right? So part of like my whole goal here is literally basically to motivate the choice of capital N. And so it's kind of like reorganizing the ideas in the proof and showing you how they're sort of true heuristically and how you can use that to get a sort of heuristic choice of capital N. So yeah, anyway, all the intuition and ideas in here are kind of like in practice the kinds of analyses that you'd use to actually formulate a proof like what they do in the book. No one actually just sat down and just wrote the proof in the book the way it is, like from scratch. They definitely, anyone who came up with this proof was definitely thinking about it somehow in a way that's similar to the kinds of things that I just talked about in this lecture. So hopefully that gives you an idea of kind of like what analysis is really like, and how powerful it can be. I think it's very cool, even though it's very complicated and hard to wrap your head around. So yeah, anyway, I hope you enjoyed, and I'll see you next week.